Hi, I'm Brian Weiss. I'm an applications engineer here at AMD Xilinx. Today, I want to teach you how to take a custom FPGA PL-based design and add AI engines into that as simply as possible and take that design into hardware 15 minutes. So this request comes up quite frequently from a lot of my customers who are maybe FPGA people, already have maybe some test pattern generators or A to D interfaces or things like that in an FPGA design and are evaluating Versal and want to understand how to take an AI engine DSP design that they've built separately and integrate that into their own custom PL design that they can exercise in a way that allows them to measure things like performance, power, and efficiency, and also simply just evaluate functionality as well on the interface. So I'm going to go through just a couple slides here to set the stage, and then I'm going to walk you through a tutorial here, just stepping through the different steps of the workflow to put this design into hardware. So this isn't going to be a deep dive on the device architecture or even the various tool flows involved here, be they Vivado or Vitis or the AI engine compiler tools. But just to give some explanation of why this is more complicated in Versal than maybe you're used to, is if you look at the device architecture, right, we kind of have the adaptable engines here, and the DSP engines here sort of comprise what you're used to as an FPGA device. This is your PL, this is your fabric, this is your FPGA logic. But you also have these ARM, these scalar engines, which comprise of multiple ARM processor complexes. There's the platform management controller, which is another set of processors that manages boot and security and power management. And then you have the AI engines, which is yet another array or matrix of processors that need to be programmed. And then there's all the hard cores down at the bottom, as well as the network on chip that connects everything together. The NOC and the memory controllers are hardened, so the boot flow has to configure these things, and where they get configured is a little bit complicated. So in order to manage all this complexity, Xilinx has put out our Vitis design tool, which ultimately ties everything together and generates a boot image for you. Well, a lot of the customers that I have simply want to look at just the PL and the AI engines together. They don't care about running software on the A cores. They don't care about using any of the hard logic, or at least the memory controllers and parts of the NOC. They simply want to evaluate AI engine and PL performance together. So that's what this is all about, how to do that. So the background motivation here for creating this tutorial is I'm assuming that you are an RTL engineer or a DSP engineer who's comfortable writing VHDL and Verilog, who has experience with the Xilinx Vivado design tool and are able to build your own IP integrator projects. I'm also assuming that you're familiar with AI engine design. Okay, I'm not going to teach you how to do AI engine design. That's a whole nother separate multi-day training class to really dive deep on the AI engine tools. And I'm also assuming that you're not interested in running any software on the APUs or the RPUs. So either of those ARM cores that I showed in the last diagram. So in this case, your use of Vitis, which I'm also assuming that you are not very familiar with at this point, and you don't know what a Vitis platform is or anything like that. At this point, your use of Vitis is really just going to be to tie the PL bit stream together with the AI engine, the binary image that gets deployed on the AI engines. Okay, so from there, you're gonna take that final output image and because you're only using those two components, it's much simpler than it actually seems if you were to start to go try to learn the full Vitis flow that involves tying in together all the rest of the software pieces. And I don't think that's necessarily terribly clear from a lot of our documentation or tutorials just how to do that in a much simpler way, but it is possible, and that's what I'm here to show you. Really is just to answer the question, how can I quickly evaluate my custom AIE and PL design in hardware using the tools that I'm comfortable with. So to really hammer home the main point of what's going to be different here in the flow that I'm going to explain, I want you to think of the traditional FPGA IP integrator design flow where you do your design entry, and once that design you're happy with your design, it's in air quotes here, it's effectively a one-step process to run an implementation and generate the bit stream. And that is you click the generate bit stream button in Vivado, and that spits out a bit stream. Now in Versal, using the Vitis design tool, that one-step process is now being broken into two steps. So rather than just clicking a generate bitstream button, once our design is done, we're going to click an export platform button, which is just going to package up the project in a way that we can pass it along to Vitis, which will be the second step. And that second step is within the design environment where you're going to add in your AI engine code. And once that AI engine code is finished, that's where you have defined all your PLIO interfaces that determine the connections between the AI engines and the PL logic. So that's why this step needs to be completed before we can generate a bit stream. So once that's all done, within the Vitis environment, you essentially click a single button there. After we set up some configuration options, you click a button and it generates a bit stream. And that's really the extent of the flow. We've taken a one-step flow and broken it into two. Okay, so the tutorial that I'm about to walk through, we're going to basically implement a low-pass filter on the AI engines that is fed from the programmable logic by a couple of sine waves that get added together. And what we're going to do is we're going to look at the PLIO interfaces, these axis stream interfaces that drive data into the AI engines and receive data from the output of the AI engines. We're going to probe those with integrated logic analyzers that we can view from the hardware manager within Vivado. And that way we can validate the behavior coming in and out, and from there it will be obvious to you how you can take performance measurements at the interfaces and measure latency and things like that. So it's not real important what we're actually implementing here, but really the design flow is what I'm trying to showcase. So the steps that we're going to go through is, first of all, we're going to create a quote unquote normal Vivado IP integrator project from scratch, and we're going to export. We're going to populate that design with all the things in the block design that we need. Then we're going to export that platform which packages it up for Vitis. Then we're going to switch design tools into the Vitis environment, into the user interface there. And we're going to create an AI engine application project. We're going to generate the boot image for that, and then we'll copy that boot image onto the SD card and run it on a VCK190. Okay, let's get started. Okay, so I've launched a Vivado 2022.2 IDE here, and we're just going to start by creating a new project. Simply click through the initial options. We're not going to make any changes at this stage other than to point to a VCK190 as the target board. Now that's going to open up a project for me. The first thing I want to do is go into the settings and check this box here that says project is an extensible Vitis platform. This is a key step. If you miss this, you'll be confused later on when we try to export the platform because you'll be missing a tab. So make sure to do this. Then we're going to create our block design here. And we're going to start adding IP, starting with the SIPs wizard. Now that the SIPs is here, I'm going to go ahead and run block automation to allow it to apply the board preset. I'm going to enable a clock and a reset. Make sure there's no memory controller not configured yet. Okay, now we're going to change a few options on the SIPs. We're going to change the PMC options. We're going to set our clock frequency to be 100 megahertz into the PL. So that's the first thing. I'll go to my output clocks. And then on the knock page, I'm going to enable the PMC to knock interface. And this is the interface that allows the PMC, which is the boot processor, to load the firmware that runs on the AI engines. So now I'm going to go ahead and add an instance of the AI engines, as well as an AXI knock. And I'm going to go ahead and run the connection automation here, leave all the defaults. It's going to wire these together. Now, one thing I have to change over here just to avoid a warning is select the SIPs here, the properties window, change the simulation model to TLM. We're not using simulation, so this doesn't matter for our purposes. All right, so now we're going to start adding in the IP for our sine wave generators. Configure this to disable the phase output, enable the output T ready, and then I'm going to make a copy of this, change the other frequency to 20 megahertz. Okay, so now what we're going to do is add a custom RTL source here, or create a custom RTL source here called Axis Adder, and it simply is going to be adding two axis stream interfaces together. It takes in two axis stream interfaces and adds the data on their T data signal together combinatorially. So I'm going to simply copy and paste the logic in here. This is not important how this works. Okay, so now that I've got this IP or this RTL added, I can simply drag it into the block design and the tool will package it up for me. Now I can connect up those axis stream interfaces. Okay, so this axis stream interface is going to get connected into the AI engine. Now on the output side, we're going to add a data width converter simply to make the tool happy so that we have an axis stream interface to connect up to. And you'll see how this works in a minute. And we're going to, so the output of the AI engine is going to feed into this data width converter, and we're just going to continually read out the output from that. Okay, so I'm going to also need a reset logic here. And we're going to drive all the clocks from the SIPs wizard. Reset is going to drive this, and then everything else gets connected from here. Okay. Now the other thing I want to show here is that you can add ILAs into here, and we'll be able to view this ILA from the hardware manager after Vitis has done its thing. these AXI streaming interfaces on both slots. Increase the depth of the storage and add some pipelining. Then I will connect this ILA, the clocks and reset, and the two inputs here are going to be my two sine wave inputs. What we're going to do is we're going to also use Vitis to insert ILAs on the actual interfaces that go into and out of the AI engines, on those PLIO interfaces. Okay, so at this point I can save my block design. I can validate the block design. And this will take a minute potentially. Okay, so validation is successful. So now what we need to do is save the block design. And then I'm going to right click, create HDL wrapper. Say OK. So the next step is to go to the platform setup tab. And again, if you're missing this tab, it's because you missed the step at the beginning to go into settings and enable the Vitis extensible platform support. So the AXI port, there has to be one master AXI port enabled on the platform. We're not using it, so it doesn't matter. The AXI stream port, so this is where we're going to tell Vitis which ports that it can manipulate. So it can talk to different AXI stream ports on our design. So we're going to check the output from the adder and the input to that data width converter. Now I'm going to give them meaningful names that we will refer to later on. To enable the clock, set it as a default. Give your platform a name. Save the design. And then export platform with this button. It's going to tell us that there's no generated IPI blocks. In order to do that, we need to come in here, right-click this block design, and say Generate Output Products. And click Generate. This will take a minute, so we'll reconvene after this is complete. Okay, now that the platform has been generated, or the block design has been generated, we can export our platform. Click Next. It's going to export for hardware. Pre-synthesis export, since we've not run synthesis yet. Leave the defaults. And finish. Now this is going to output a file called an XSA file, which is an archive that contains the block design, as well as all the sources and everything that Vitis will need to recreate that block design, modify it as needed, and generate the final device image. So the next step from here is going to be to do that step 2 of that process that I explained. So we're going to switch from Vivado and use Vitis. Okay, so I've launched Vitis by simply running the Vitis command here, pointing it to my workspace. It has launched the IDE, which is blank, brand new project. I'm just going to close the banner window, say File, New Application Project. Skip this page, click Next. So this is where I'm going to specify the platform that I'm targeting, and that's what we just created from Vivado, essentially, is the platform. Or we want to create a new platform from that XSA file. So to do that, we can provide our path to our XSA file here. Click Browse, and when the window shows up here, we can navigate to our XSA file, which is back in our Vivado project structure. Once the platform file has been created from the XSA, we can click Next. Now we create the name of our application project. This is going to be that fur filter. And it's going to be targeting the AI engine processor domain. Leave these as default. Empty application, and choose Finish. So this is going to set up a Vitis project for you. This one right here in the red, targeting the AI engine runtime, is where we're going to specify our AI engine graph code. Okay, and I'm simply going to copy and paste AI engine graph code from our DSP-lib tutorial. This is simply generating a single rate symmetric fur filter using DSP-lib. Okay, now we need to set up the AI engine compiler so that it knows where to find the DSP library. Sorry, I missed a step. We need to change this from, before we do this, we want to target hardware, not hardware emulation. So I'm going to come down here, change this, right click on hardware, say set active. Now I'm going to go ahead and add those paths into the compiler settings. Okay, we're going to specify our top level file from the workspace here, which is that graph CPP file. All right, so now our AI engine filter is ready to build. We're going to go ahead and press the build button here to compile the AI engine filter. Okay, now that our AI engine compiler has completed, we can see that in the hardware directory is the lib.adf file. That's the final binary that gets loaded to the AI engines. So now we have that AI engine binary and we have our platform. Now we need to tell Vitis how it needs to hook up the PL into our AI engine. So our AI engine has these PLIO definitions titled data in 1, data out 1. That combined with those names of those AXI stream interfaces from the Vivado platform export, those two pieces of information are needed to tie these things together. So to do that, we're going to go to the hardware link project, part of the project up here. There's a PRJ file, and we're going to right click this binary container and say edit V++ options. Now in this V++ configuration settings, I can choose the ellipses here, and I can add in my connectivity information. The syntax here is well documented. Refer to the Vitis application acceleration user guide for the description here, but essentially we're defining a section that defines the connectivity. We're making streaming type connections from M-axis adder. If you remember, that was the name that I used in Vivado for the output interface of the adder when exporting the platform. And then AI Engine 0 here is the instance of that IP, of the AI Engine IP in Vivado. And data in 1 is that PLIO interface that I want to connect it to. Similarly, on the output side, the AI Engine data out 1 is the PLIO interface, and that's going to drive that data width converter, the input to that. Okay, so I'm going to say OK here. Say apply and close. Now, one other step I want to do is insert ILAs onto those AxiStream interfaces. So to do that, I'm going to choose, right-click on the hardware link project, say C, C++ build settings, and I'm going to add flags to the Vitis linker to do that. It's as simple as adding the -debug.aie.chipscope flag and pointing it to the PLIO interfaces that I want to connect. I can say apply and close. And now this design is ready to link. So I can select the hardware link project and choose the build icon. Now this step is going to take a while because at this point the Vitis tool is going to open the Vivado project. It's going to instrument it as we just described, and then it's going to actually run through synthesis and implementation. So after this step completes, we'll reconvene to finish the flow. Okay, now the Vitis link stage is complete. Place and route has been run, and we have a PDI image, which contains the bitstream and some of the other boot artifacts that we'll need. I wanted to show real quick that you can look underneath this hardware link project. I can drop it down. Now I've got this binary container build directory. I can push down into here and link Vivado, VPL, proj, and there is a Vivado project right here. And this is the post-link Vivado project. If I double click on this, that will open up another Vivado project here, which, as you can see, now contains both of our PLIO interfaces are now enabled on the AI engine, and they are hooked up to the interfaces according to that connectivity file that we specified earlier. You'll also see that it's added these extra slots onto our ILA according to those debug AIE chip scope switches that we added. And this is the design that finally gets run through implementation to generate the PDI file I mentioned before. So one other thing I'll note here is that the tool also added these data width converters. That's because the output of my AxiStream adder is only 16 bits, and the PLIO interfaces that I've configured are configured for 64 bits. So the tool automatically inferred these. Okay, so at this point, the last step to be run is simply to package up the boot image. To do that, I'm going to right-click, I'm going to select the FIR filter system and choose the build button here. Okay, once this step is complete, we're finished. In right about 15 minutes, give or take, we've gone from complete scratch design, custom PL design, no pre-built platforms. We've exported that platform that we built ourselves, imported that into Vitis, created our own project, and ran through the whole Vitis flow. So at this point, we now have inside the hardware link directory, inside the hardware directory of the FIR filter system, there's a package directory, and this is where my SD card contents are. So there's a boot.bin, there's an image file if you prefer. So at this point, we can go copy those files uh, into our SD card. So that exists in my workspace, system, hardware, package, boot.bin. Copy that to the SD card. Checked that. And now I'm inserting that SD card into the VCK 190 on my board, or on my desk here. And I have a serial terminal open here. So now when I power on the VCK 190, you will see that the boot images are displayed. Okay, so now I'm going to simply go back to the original Vivado project where we started from. Open my hardware manager. I'm going to connect to my board here. Then I can specify my probes file, which this is going to now exist inside my Vitis workspace, inside the hardware link directory, and inside the binary container 1 directory. So when this opens up, I can run an immediate trigger. I can see all 4 of those interfaces. And if I drop those down and configure the waveforms here a little bit, as you can see, I have what looks like some sine waves here on the inputs of varying frequencies. These are my 2 input channels, and then the input and output of the AI engines are probed. You can see the waveforms a little bit funny looking because of those data width converters. We're looking at the 64-bit interface here, so they look a little bit funny on the input and output, but you get the idea in terms of probing at different stages of your design using the ILAs. Okay, so that completes this tutorial. As we've shown, you can very quickly and easily start from an FPGA design, add your AI engine code into it, and connect that up through the Vitis tool. It does not necessarily have to include all the steps that are usually included in a lot of the other public tutorials that are out there for showing the Vitis flow with AI engines that involve building Linux and building all the boot image software manually and all that stuff. In this case, we're not using that. We went through this flow very, very simply. Now, one bonus follow-up question you might have is, okay, now I want to go make a change to my FPGA design. How would I go about doing that? I may save this for another video, but just to highlight real quickly, it's relatively simple. So I would simply make whatever changes I wanted to in this block design, save it, validate it, do that normal block design flow. And then once that's done, I come back in here into my platform setup tab, and this page will reflect any changes I've made in the block design. So any clocks that I've added will show up in the clock window here, and any AXI interfaces or AXI stream interfaces I want to connect up to, they'll dynamically update in this tab, in this page, so I can add and remove things as needed. But at the end of the day, once I've made all my changes, I simply re-export the platform. That will update that XSA file that we've been using. And then I simply come back here into Vitis, and if you see there's this Design 1 wrapper project here within this overall project. This is what represents that platform and what is generated based on that XSA file. So if that XSA file updates, all I need to do is come into here, right click on that and say update hardware specification. And now I will see a window pre-populated with the XSA file. Now that that's been updated, I simply say OK here. And then all of the projects will go out of date. And I can simply rerun this build from the start here. And that will generate the whole thing. OK? All right. Hopefully that is useful to you. That concludes this tutorial. Thank you very much.